Hey everyone, in this series of slides, we're going to talk about differential functioning effect sizes. And we're going to talk about these both at the item level and the scale level or test level. And first off, the good question is why are we doing this, right? And so a lot of times in the past, the way people have thought about invariance is kind of like you're testing to see if you have apples and oranges, right? Do the items function the same for different groups of people? And the idea was that if the items are functioning different for different groups, well, you really can't compare the results. And you see this really going back to a lot of the thinking, looking at both confirmatory factor analysis and item response theory, really starting in like the 60s and 70s up through really the 2000s. And the notion was, well, you want to know if these things work the same way for different groups. You're going to do this test, and the test will tell you, do you have an apples and oranges situation, or do you have two different sizes of oranges that you can compare meaningfully? And one of the issues associated with that, though, and a lot of my earlier work in my own career, looking especially at the likelihood ratio test, is that the significance test used to test for invariance are prone to a lot of the same issues that normal statistics are. So if you think about a t-test or a correlation, right, they're prone very much to the power is very much determined by the sample size. So a t-test with 1 million people will have significant yet practically meaningless results. And the same with correlation, right? A correlation of 0.02 can be statistically significant if you've got just an enormous sample size. So the similar kind of thing happens with a good ratio test. And since we're talking about item response theory, we're typically dealing with some fairly enormous sample sizes. Not unusual to see sample sizes in the thousands, and those tests are going to be very high powered. And so the issue then becomes, well, if you have diff, or you have differential functioning at the test level, what does that mean for making comparisons amongst groups? In other words, is that diff meaningful? Um, like same with the correlation analogy, a correlation of 0.6 is going to be meaningful, and a correlation of 0.02 probably won't be, but it may be statistically significant with a really large sample. So that's kind of what we're trying to do with effect sizes. We're trying to say, well, how much dip do we actually have here? How much does it actually matter? And I'm not saying that you would then ignore a dip that exists, but you might be able to explain the nature of it, and you might be able to explain approximately how much difference in the data, raw numbers in the data, that you might expect to see from diff or differential functioning alone. So in order to do this, we've got to set up this notion of expected scores. And expected scores is something we've been talking about all semester in various forms. The expected scores are going to give us a meaningful metric to talk about how much diff or differential functioning at the test level is present. And hopefully you've done the readings by now. You're kind of aware of where I'm going with this. I'm going to go over to the graph sheet now. And I'm going to go way back to one of the first graphs we look at in this class. This is the two-parameter model item characteristic curve. And what we got here is the probability of getting the item correct given different levels of data. And this is, in effect, something of an expected score. And we've kind of used this analogy all semester to say, well, what would you expect somebody to get in this item if their theta is a 1? And the way we've kind of talked about this, well, imagine you had 100 items. And all 100 items were exactly like this. If the probability of getting this item correct is 0.5, we would expect the person to get half the items right, or 50 items out of 100. And so 50 would be the expected score if we were to have a test composed of 100 items just like this. So in some ways, the expected score at the item level is 0.5, but the problem is that doesn't make any sense, right, for a dichotomous item, because it can only be a 0 or a 1. So it only makes sense if you start talking about like 100 items of these such items. And so we're much more used to talking about the expected test score and the test characteristic curve. And I'll pull up that graph we looked at earlier too, where the test characteristics curve is just the sum of all four, in this case, item characteristic curves. And we were saying that, with the theta of 1, you calculate the probability of getting the item correct, or the observed score. And this axis over here is completely wrong. That shouldn't say theta. It should say, the kind of the number correct or what have you. So this is a kind of a notion that's been going back for some time now. And one thing we haven't talked about, but we can also compute expected scores based on the graded response model fairly easily. And I'm going to show you a graph here that will do just that. So this is let me make this a little bigger. This is the graded response model where we've got an A parameter, in this case it's 2, and we've got 4 B parameters. So this would be a single item with 5 response options. And what we can do is we can compute the BRFs, from this formula. And the formula we looked at earlier in the semester, I don't think I have it on the sheet, but we can compute the probability of, and the BRF values, and then the probability using the formula you see right there, right? It's A times theta minus B over 1 plus A times theta minus B, and to the exponent, of course. And then we can compute the category response curves that we've been looking at, where these p-values are right here. And that's what's graphed on here. And again, this is nothing new. We've been looking at this for a while now. And you can see the probability of putting a 1 versus a 2 versus a 3 versus a 4 versus a 5, given theta. And so then what we can do is we can translate that into an actual expected score. And the formula for doing that is right here. It's the sum across the different response options from 1 to m of the probability of putting that response option. So probability for the item, so I is the item, right? K is the response option in this case. So K goes from 1, the lowest response option, up to m, the highest response option. So it's the probability of putting the response option. So the first time through, let's say we're considering response option of 1, somebody put a 1, probability of putting that 1 for this item given theta, which is just computed to given theta, so it's just one p-value there, times the actual response option x ik. So that's the actual value. So that would be just a 1. So it would be 1 times that p-value, and then for 2, it would be the probability of putting a 2 given theta, right? And times a 2, just the number 2. And then for 3, be the probability of putting a 3 given theta times a 3. And we do that and we sum across all those p times the actual values here. So let me pull this up on the sheet. So over here you can see I typed in just the actual value, 1, 2, 3, 4, and 5. So the expected score in this case is the probability of putting a 1 times a 1, right? And you can see that in the first part here, P3 times K3, plus the probability of putting a 2 times the number 2, plus the probability of putting a 3 times the number 3, on and so forth, up through 4 and 5. And then you sum that up and you get a number that's going to range on the low end from the lowest response option, which in this case is a 1, up to the highest, which is a 5. So you can see when theta is a positive 4, the probability is expected score is a 5. So this is a really nice framework for us to talk about how these p-values map onto an actual observed response. Now, again, in practice, somebody could only choose a 1, 2, 3, 4, 5. They can't choose these decimal numbers, but we still say this is the expected score. And just like before, we would imagine if we had an infinite number of these or 100 of these, right? The average across those 100 values would be this, and then it could take on a decimal. So those are the expectation, the expected score, aka the true score. Some people call it, like Raju calls it, a true score, and non-Raju's work really is borrowed heavily from in my own thinking about these effect sizes that I talk about. And some of these things he actually came up with, and I just took it and then expanded on it somewhat. So he talks about it as a true score. I tend to prefer the term expected score just because it's really, I think, a bit more accurate. It's the expectation, right? There really is no notion of a true score, because I think that kind of confounds item response theory and classical test theory. And true score is really a concept pulled from classical test theory. So I like expected scores. Just like we've been talking about the test characteristic curves and expected score. You can think about ICCs as expected scores, and so I think it lends itself, pretty naturally to an extension of what we're doing here. So hopefully everybody sees how we got that. Again, this is all stuff we've done before. Compute your BRFs using the formula, literally to write out of the book, and then compute the probability of each category response. You can see for the lowest, it's 1 minus that first BRF, and for the highest, it's just equal to that last BRF, right? Just kind of pulled equally from this column over here. And the other three here are just differences between the BRFs. And then we take that p-value, multiply it times the actual observed response, and then add that up. So you can see that here, right? It's the p1 times 1 plus p2 times 2 plus P3 times 3. Yeah, you get the idea. And then you sum those things up and you get this expected score.